Okay, we're ready to kick off?
Yeah.
All right. So welcome everyone and thank you for joining us. The VCTF and C4Net are delighted to have you here today. Given that we're meeting virtually and that we're on many lands, I'd like to acknowledge the Wurundjeri Woi-wurrung people as the traditional owners and original custodians of the land that I'm on, and the traditional owners and custodians of the land where you are, and pay our respects to their elders past, present, and emerging. The Center for New Energy Technologies, or C4Net, is a member-based organization tackling the complex sector-wide challenges of the transition that's upon us. The center is generously supported by the collaborative works of industry and academic institution members, the Victorian government, and research sponsors, and we're a proud sponsor of this project today. This webinar is jointly brought to you by C4Net and one of our long-term sponsors, the Victorian Clean Tech Fund. VCTF is a Victorian fund that provides financial and management support for early-stage enterprises. It generally invests in pre-seed and seed funding phases where traditional venture capital sources aren't readily available. Originally funded by the Victorian government, VCTF promotes employment growth in Victorian clean tech startups, whether the startups are challenging incumbents or partnering with them and leapfrogging mindsets and established processes. The collaboration on innovation in the energy sector can be a challenge, and we're delighted to have some of VCTF's key stakeholders here on the webinar today. This session shares some of the insights from the C4Net sponsored project, model-free operating envelopes at the NMI level. We know that we're in an energy transition, and increasing penetration of distributed energy resources at the low voltage level requires DNSPs to have more detailed visibility into those LV networks. And in the past, this has required employing electrical models of LV circuit modeling, including impedances and phase connectivity, nodal placement, etc., which can be complex and time-consuming and sometimes inaccurate. Researchers from the University of Melbourne have created innovative model-free methodologies to help operators get real-time capacities for LV networks. And today we have Professor Nando Ochoa, Mr. Vincenzo Bassi, Dr. Dylan Daglaw, Professor Tanzu Alpkan, and Professor Chris Leckie on how they're using neural networks to create the electricity markets of tomorrow. Nando, over to you.
Thank you very much for that kind introduction, Chica. Good morning, good afternoon, good evening, everyone that is joining us, not just in Australia, but around the world. Thank you for joining us today. So the title, you know what we're going to talk about today, which is a potential avenue of how we're going to do hosting capacity assessments for distributed energy resources in the future, and potentially as well how we are going to calculate operating envelopes in the future, all without power flows, which is a very exciting proposition, a very challenging one as well, but one that might be needed if we want to really not just make the most of smart meter data that is available in places like Victoria, of course, and in many other parts of the world, but also because there are so many challenges with the modeling of particularly low voltage networks, a very part of the distribution network that is connecting our houses, our businesses. So today, just because of this is a webinar, just for you to put some faces there, the main speakers today will be myself, Vincenzo, and Dylan, but the whole team includes Tansu and Chris as well. Their expertise in machine learning and artificial intelligence as well has been critical, so they will be here as well to answer questions at a later stage. And as per my earlier slide, please do use the Q&A there. Put your comments or questions there in the chat. We will have time at the end of this presentation to go through that. So let's start. The structure here today is one that I hope will work. The idea here is first for you to understand why do we need to calculate voltages in networks in the context of distributed energy resources, solar photovoltaics, electric vehicles, batteries, you name it, different technologies. Why we need those calculations and how we do them today. With that, I will try to persuade you that there might be a different way of doing things, and that is our model-free approach, or more precisely, electrical model-free approach. There will be a model, of course. We're talking about neural networks here, so there's a model, but an electrical model-free approach. We'll then move on to the smart meter data, real smart meter data from the different partners here in the C4Net funded project. So we have data from OSNet Services, data from Gemini, data from United Energy. And we will discuss the data, the nature of the data, some of the challenges as well as the data. And then we will move on to the model-free calculation. So we're going to show here some interesting applications using the real data, particularly from Gemini, as one of the case studies to assess the connection request. What if someone wants to connect a 5 kilowatt photovoltaic system? Is it okay or no? So we are going to present that application. What about hosting capacity? How many houses can actually have that 5 kilowatt PV system, for instance? Or even operating envelopes. What if we, in the future, because the infrastructure is not yet there for that sort of application, but if we want to calculate them, we all want to demonstrate how to calculate it without electrical models. So we were going to present as well an operating envelope calculation, and then we're going to finish some key remarks. Different parts of the presentation, I will comment all the different challenges, because as exciting as this topic is, this area really of extracting value from smart meter data for very technical applications, these are the first steps. So we're going to share very exciting findings that we have, but still there's a lot to do. We are only I think it is 9 months in a 2-year project. So we're very pleased to really share everything that we're going to share today, but there's much more work to do. All right, so let's continue. Let's start first with voltage calculations and distributed energy resources. So let's get to the basics. When we design low voltage networks, okay, our poles and wires connecting our homes, we do them in a way that we estimate what is happening with the houses in general, and then we plan the different conductors and transformers, and such that at all times our voltages are going to be within the statutory limits, the local statutory limits, and the currents are not going to exceed the ampacity of the corresponding assets. All good. The challenge is when we have different new technologies, such as solar photovoltaics or electric vehicles, we will have different flows. In the case of solar photovoltaics, we will have reverse power flows when people are not at home, and that can increase the voltages or even exceed as well, the currents that are the maximum currents of the corresponding assets there. If it is electric vehicles, you will have voltage drops, is the opposite, and you can have even also more currents, because if the electric vehicles are charged at night, with people come back from work, if they're not working from home, of course, then you will have a coincidence, and then that can raise some impacts. Now, because of this is absolutely normal for distribution engineers and planners as well of distribution networks to always keep assessing, what would be those maximum exports in the case of solar photovoltaics, or the maximum imports as well in the case of electric vehicles. Always trying to understand what are the effects on the network, so as to know that we are not exceeding those limits. So we always need to know what are those maximum values from a planning perspective, or also from an operational perspective, right? Now, how do we do these calculations then? So today, what you would like everyone to do, of course, is using electrical network models. In reality, we don't have those electrical models, particularly when it comes to low voltage networks. Some companies do have them with some limitations. Some companies do not have them. So it's a mix and match, if you want. At the higher voltage levels, or what it is called international medium voltage, we're talking about 11 kV, 22 kV, 33 kV, those models exist, but at low voltage is not the case. But let's suppose that we do have those low voltage networks, the electrical models. What we will do to assess the voltages. So first, you define a scenario that you want to check. So if we're talking about solar photovoltaics, of course, the critical moment is not at midnight, because at midnight we don't have sun. So you pick midday, right? So a lot of generation. And at that time, if people are not working from home, COVID has changed a lot, you will consider that is minimum demand, right? So you will consider minimum demand for many customers. Then you will consider the exports that you might see, from those customers that you want to assess, where they're going to have a significant voltage rise or not. You will have, because if it is a network, you will have a voltage at the reference bus, your transformer, if you're just modeling the transformer there of that LV part of the network. Then what would you do? Well, you have to have your electrical model, of course, topology, impedances, phase grouping, everything, right? And these impedances, of course, we're not talking about single phase. It's a full 3-phase network that in reality it has a neutral and has grounded, all right, if you really want to be precise. Now, after that, what do? You have to run three-phase power flows, all right? It cannot be balanced because it's not a balanced network. So for instance, you can use OpenDSS. Shout out there to my colleagues in EPRI in America. So you can use any other tool, of course, but it has to be a three-phase power flow simulation if you want to do it properly. And then, of course, you check the voltages because you run a power flow, you check the voltages, and if the voltages are okay, and if you're running, for instance, a hosting capacity, if the voltages are okay, so you would put a harder scenario, like more houses with photovoltaics, for instance. But if the voltages are not okay, it means that you reach what you wanted. So that's your hosting capacity. The same process applies for operating envelopes. The same process applies for anything else. So this is what we do today, all right? Now, of course, because the low voltage part of distribution networks across the world are becoming so important because of all these residential resources that we're having these days. In Australia, almost 1 in 4 houses have photovoltaics. Then it means that having these electrical network models, particularly in the low voltage, is very important, right? And because of that, distribution companies, not just in Australia, but around the world, they are starting to produce these LV network models, which is great, all right? There's nothing wrong with that. Actually, it's fantastic. However, it can be extremely time consuming, expensive if you want to get it right, because you need to send people sometimes, to check. And unfortunately, even if you do that, will not be 100% accurate. There's always some errors in topologies. There's always some errors in phase groupings, errors in impedances. The neutral is very difficult to tell, how the neutral is actually being used, or even the grounding, where exactly, the neutral has been grounded. So it's very difficult to have it 100% accurate, right? So what if we could calculate voltages without electrical models? Now, at this stage, some of you might be asking, Nando, but it's not just about voltages, right? I mean, you have the flows, you have the KVAs, well, what about that? Well, I mean, the reality is that when it comes to thermal aspects, it's very simple, or simpler than voltages, all right? Why? Because the thermal aspects, you can just deal with them by just adding up values. It's not going to be exactly the same because you have losses, all right? But it's relatively simple in that sense compared to voltages. Voltages is just totally non-linear. So that's why our focus is with voltages. Now, back to my question here on this slide. What if we could calculate voltages without electric models? That is our model-free approach. And well, there's a lot of work that has been done in the last year or so, and we're releasing, of course, the corresponding reports. And yeah, we have some papers as well coming along. So let me tell you a little bit more about this model-free approach. So in terms of a scenario, you still have to define your scenario that you want to calculate the voltages for, right? And of course, you will calculate the voltages and you will assess and create hardware scenarios. But instead of power flows and having the electrical model, now we have some clever stuff that captures the physics of the low voltage network. So we're using neural networks that will be trained with historical smart meter data, right? Now, what is the advantage of doing this? It will remove the time and cost associated with the production of LV models, and can be also an extremely quick alternative to power flow based techniques. So the way that you actually, once you have a neural network that is trained and you have the P and Q values, the calculation of the voltages is extremely quick. Actually, as a matter of fact, it's quicker than any power flow because the power flow is an iterative process, right? So that can be a very powerful thing. On top of that, what we are doing as well doesn't require the voltage at the reference bus. Now, of course, some of our research is telling us that if you have it, of course, that would be great, but we can do it without, which is great. All right, so this is the context of why we have this project, the model-free operating envelopes at NMI level. That's the link to our project. You perhaps already have it, in the invitation there to this webinar. Now, let me get a little bit more into the approach, into the details. Of course, I mentioned already neural networks, all right? So what is the basics of neural networks? The basic of a neural network, or the very, very basic, if you want, is the neuron, right? So you have a set of inputs that then are mixed through a bias and activation function to produce an output, right? Now, if you have a set of neurons that are organized in a systematic way, well, you have a neural network that have multiple hidden layers or just one. Well, you have the inputs and outputs, and you want to relate those inputs to outputs. At first, you relate them considering the historical data, so what has already happened. And once you create those relationships, then you can actually use it to produce outputs based on new inputs. That's the idea. And how do we relate this? Well, we need to do it in the best way that captures the nonlinearities of that particular low voltage network, right? Our inputs are going to be the smart meter data, active and reactive power, and our outputs, of course, the voltages, the magnitudes of the voltages at the connection point of the customers. So the training, we use historical data to produce that neural network that really links the inputs, the P and Q, with the outputs, the voltage, all historical data, all right? Once trained, we're ready to calculate voltages based on any set of active and reactive power. And voila, once you have that, well, you can do your hosting capacity assessment, your connection request assessment, or even operating envelopes. Now, let's get into more details, and I will pass the word here to Vincenzo.
All right, so I'm going to go into a little bit more of details about our model-free approach. So the methodology can be divided in three main stages. I'm going to enter in details of each of these three main stages later. But first, we have our smart meter data that, as Nando was mentioned, is comprised of active power, reactive power, and voltage magnitudes, which is historical data. Then we use our historical data through a neural network selection process, in which we define the most suitable neural network for the studied low voltage network. And with this, the most suitable neural network, once trained, we can use it for our model-free voltage calculations. In below, again, are all the reports and papers that we have produced during this research. Next slide, please. So in terms of, for each of the three stages, I'm going to describe it in steps. So first, for the smart meter data, the first step is to collect the historical per phase smart meter data of customers. Then the second step is to pre-process the historical smart meter data to obtain active powers and reactive powers values for each of the customers. The third step is to build the training dataset, which is comprised of active power, reactive power, and voltage magnitudes. With this data, we go to our second stage, which is the neural network selection process. And here, the first step is step number 4 for the entire process, is to define the hyperparameters and neural network characteristics that are given by the nature of the problem, which is basically a regression problem. So the input layer dimension is going to be twice the number of customers because we consider customers' active and reactive powers. The output layer dimension is going to be the number of customers because the outputs are the voltages of all customers. The output layer activation function is going to be linear, and the loss function is going to be the mid-square error, which is typically used for regression problems. We are going to scale our data to values within 0 and 1 to accelerate and facilitate the learning and convergence processes. And we're going to use the Adam optimizer because its suitability to a wide range of machine learning problems. Next slide, please. So in terms of then we go for step number 5, in which we define search spaces for the remaining hyperparameters, which is the number of hidden layers, the number of neurons and activation functions in each of the hidden layers, the learning rate, the batch size, the epochs, and so on. And with this search spaces defined, we go for step 6, in which we carry out a k-fold cross-validation, considering all the combinations of hyperparameters defined in the search spaces in the previous step. And in here, we select the hyperparameter with the lowest root mean square error for the k-fold cross-validation. So in the lowest left part, we have a schematic of this k-fold cross-validation process. And basically what we do is we take our training data set, which is historical data, we divide it in different folds from the same length, and we use, let's say we divide it in k folds. So we run we train k neural network with different folds for training and the remaining one for validation, in a way in which we use each fold as validation fold once. And then with this, we calculate the root mean square error for the k fold, and we define the most suitable hyperparameter combination for this study low voltage network. Next slide, please. So then, once we define this hyperparameter combination, we go for step 7, in which 10 neural networks are trained from scratch with the hyperparameters that we define in step 6. And here we take the neural network with the lowest root mean square error in training, and we define our final neural network ready for our model-free voltage calculations. In terms of the last stage of the methodology, the model-free voltage calculations itself, we have step 8, in which voltages can be calculated by specifying only customers' active and reactive powers. So In terms of the implementation of our methodology, all that we use is basically open source softwares. So we use the Keras Deep Learning API, which is written in Python and works on top of the machine learning engine, which is TensorFlow. And now I'm going to leave you with Nando for some challenges that we have found for the NSPs.
Well, of course, so far you have here is the general methodology and what we're going to use this for, right? Now, what you have heard as well is that we need data. And data is challenging all the time in any sector. So let me just discuss some of the challenges. I will discuss a few more later that distribution companies will face, if they want to pursue this avenue. Of course, the first thing is you need smart meter data from all the customers. So if we're talking about an LV circuit, like you can imagine a street with houses, you need the data from all these houses, all right? Now, what we are going to show, for instance, with the results with Gemini is that we don't need to just limit ourselves to just one street. It can be multiple streets, but all of them associated to the same transformer. Still, but it has to be all the customers in that group, right? That is challenging because depending on the part of the world that you are, when we say smart meter data, well, that data for small customers, us in our homes, might be managed by one entity, but for the big customers might be a separate entity. That happens in Victoria, for instance. So the big customers, a big shop, for instance, three-phase customer might not have a smart meter data that is managed by the distribution companies. And then that creates, a bit of a challenge, in recovering that data, for these purposes. Now, other parts of the world, of course, the smart meter deployment, even including Australia, outside Victoria, the smart meter is happening, deployment, but it's not happening extremely fast. So if you have houses that do not have the data, then how do you do it? Well, we hope that perhaps we might be able to find a way of covering with data gaps, but for now, we need all this data. Now, also, well, as I was mentioning, well, we have the same customers, and well, I already mentioned that. But another aspect is the data. It's not that all the customers have to have the data. The data needs to be good, right? And one critical thing, to really use this technique, because as I mentioned earlier, we are trying to extract the physics. If we are trying to extract the physics of a network, that network cannot be changing. And the reality is that, not every day, but after a few years or a few months, a street that had a big house at the very end, that house after 6 months can become multiple tiny houses, right? That is a topological change. For whatever reason, the company decided to change part of the conductors to bigger conductors because they were just very old. That, again, is a topological change. Well, not topological per se, but it's changing impedances, it's changing the physics. So this data needs to really be for a period or from a period, the historical data, where that particular network or set of networks haven't had any topological changes, no changes in the physics, no impedances, no topological changes. Now, we're talking about real data, and we're going to show you, some of in the next slides. Dylan will show you, some of the general views of the data because we cannot get into so much detail because we don't have so much time. But what you're going to see is that we will need to filter out as well part of the data. Why? Because this is real data, and with real data you can have some challenges because not just of noise, but also metering errors or just situations where the meters are recording during a fault events and things like this. All right, so we need to filter this, and that means that an initial volume of 1,000 points can become actually half of it, or perhaps a little bit less or a little bit more depending on that type of data. And then there's another challenge as well. So we're talking about data, but hey, Nando team, how much data do you need? Well, first of all, it depends on the granularity and the part of the world that you are and how this granularity exists. So the data that we're using from the distribution companies in Victoria are 5-minute resolution data, which is pretty awesome, right? However, of course, still, even if it's 5 minutes or 10 minutes, how much data do you need? Well, that is part of the research, but you will need a minimum amount of data, right? And we'll discuss this a little bit later. At the end of the day, what I wanted to say is that, yes, we are aware of all these challenges. The companies working with us are very aware of all these challenges. But, well, we hope that our ongoing research will address some of these challenges. Dylan.
Thank you, Nando. So now I'm just going to present what Nando and Vincenzo was talking about, the first stage of the process where we have to really process this smart meter data. And just a reminder, as Nando mentioned, like this is the real world, so there are lots of challenges with the data, and hopefully we can show you a little bit more of that right now. So next slide, please. So here we have an overview of the data that we receive for the three DNSPs, and it's broken down by the distribution transformers and the low voltage circuits. So for the case of Gemini and United Energy, we have around 1 year of data, and then for HOSNET, about half of that. But what's important here is we're not directly given P and Q per se, which is the inputs to the model-free approach. So we need to determine this P and Q. And it's not as simple as just extracting it from the smart meter. So for example, if you look at the case for United Energy and Gemini, the imaginary and the real components of the current is not directly given, and that's how we determine the P and Q. So we need to determine this. And what the point here is that we need to pre-process this data, the currents and the voltages, to determine the P and Q, and then filter, as Nando was mentioning, which I'll show you as well, filter some of these noise that we're seeing in the data. So next slide, please, Nando. So here we look at the voltages, the top 3 plots for each DNSPs, and the currents, bottom 3 plots for each of the DNSPs. And we can see, so let's focus on the voltages, for example. We can see that for the majority of the time, the voltages are within the limits and they seem like sensible voltages. However, next animation, please, Nando. So however, if we look carefully, we can see that there are instances of abnormal voltages. And what do we mean by abnormal voltages? Well, we can see, for example, for the case of Gemini, top left plot, we're seeing voltages as low as less than 100 volts. Now, this can be due to different things. For example, a fault, it can be to the meter just registering a non-synchronous value. It can be due to many things, but the thing here is these are not a true representation of the customer's behavior, and then they must be removed. And why they must be removed? Because we need to have a sensible starting working point of data to be used for the model-free approach. And similarly, you can see what Nando was mentioning as well. We have these challenges with the currents as high as you can see there. It's very, very light, but as high as 250 amperes. Of course, for a single phase customer, 250 amperes is not very, not something we would expect, so that we need to remove that. And then if you look at HOSNET on the right-hand side, there's gaps in the data as well. So we need to prepare and treat for these gaps properly because we want the data to be sensible. So next slide, please. On that note of filtering, so here we show, I mean, it's a lot of things going on here, but we want to show like what happens when we apply these filtering to ensure that the working data set that we have is sensible. So as Nando mentioned, we can have different time steps, for example. We can have 5 minutes, 30 minutes, whatever, right? So let's just use a 5-minute example. What we mean by a valid instance is that for all customers that we're considering, for that 5 minutes, we needed to have a voltage, a P, a real power, and a Q, a reactive power. So that's what we mean by a valid instance. And what we can see here is given the total instances, the table on the top, you can see that once we perform that filter to have the valid instances, we can see that the percentages of what we left with reduces. And what does this mean? Well, we'll show a little bit more of what this means in terms of how much data is needed. And then finally, in the table in the bottom, you can see, so what we found is that, and that's what we discussed as well, is that there was a change in the network. And in this case, there was an addition of a new customer for the case of Gemini. And having considered this change in the network, a new customer, we need to now treat for that. And then what this means is that the equivalent weeks of the data that's left, the valid data that's left, it reduces. So that's some of the challenges we can see with dealing with real data, right? So the final valid instances, it's few in comparison to what we were given as the whole working data set. And this is what's needed for the training and the testing of the neural networks. So next slide, please. Now, in these plots, we're going into the analysis of the data, right? So in these plots, we show the reactive power on the y-axis and the real power on the x-axis, right? So now, there's a lot of things going on here. So we separated by 3 times of day, midnight, midday, and evening peak, going from left to right. And then from the 3 DNSPs, so top 3, middle 3, bottom 3. So Why do we show this? Well, first of all, as I mentioned, we don't directly have P and Q. So we need to do some sense checks to ensure that we got the data right. The first obvious thing to check for is that we don't have PV generation in the midnight, because that would indicate that we have some sort of error in the data. So that which you can see in the top left plot, at midnight, or actually all of the left plots, we do not have PV generation at midnight. So yeah, good. So we got that part of the data correct. And then, you know, we can do other things and look, which I'll show you in the next slide, as to what we can see when we visualize the data in this way. And what we see as well is that the reactive power can be capacitive or inductive throughout the proportion of the day. So yeah, so keep that in mind. Now, just as a reminder, this is showing you the time analysis for all customers. Now let's look at what happens, or what we see when we do the analysis, or we visualize the behavior for a single customer. Next slide, please. Thank you. So reminder again, the data shown now is for a single customer, and we show two sets of plots, the Q versus P, so reactive power versus real power on the top, and then the voltage versus the reactive power on the bottom. Just a quick reminder, because it's not stated here as obvious as before. Positive means absorbing, and negative means injecting. So with that in mind, what we see here. So, you know, we have all these talks about the volt-var response, and what we see is exactly that volt-var response occurring here. So if we focus, it's very evident for United Energy. So the middle plots. In the bottom, we can see as the voltage increase due to PV generation, because this network has a lot of PV generation, the inverters consume reactive power. You can see that shape A, it starts consuming reactive power up to what the maximum reactive power consumption is for that given voltage. And then we can see that the reactive power consumption is maximum, and then for any further increase in voltage. And what this shows here is a very, very clear volt-var response. So this is some of the interesting things that we're seeing dealing with the data, for example. All right, so now you have seen a little taste of what we have or what we deal with the data. I will pass you on to Vincenzo, unless you want to add something here, Nando, with the data. You're muted.
Yep, no, that's perfectly fine. Thank you.
Well, thank you. So I'll pass you on to Vincenzo now.
So I'm going to present our case study for model-free voltage calculations. So next slide, please. So the case study that we are going to present today is based on the smart meter data that we received from Gemini. So the site is one distribution transformer with 3 low voltage circuits. The number of customers that we have is that we have a total of 170 customers, from which 156 are single phase customers, and 13 of them they count with PV systems, so which represent an 8% of PV penetration in this low voltage network. We also have 14 three-phase customers, and I'm going to answer one of the questions that I have seen in the Q&A section already, is that we consider each three-phase customers as 3 independent single-phase customers. So the neural network is going to see a total of 198 customers in this particular case, from which 156 are the single-phase customers and 3 times the 14 three-phase customers that we see. The resolution of the data that we use is 5 minutes, active reactive powers and voltage magnitudes. And the training data that we are going to use is equivalent to around 6 weeks. Also, the test data that we are going to use is equivalent to around 3 weeks. So the first objective of this part is to produce a single neural network for all 3 low voltage circuits connected to the same distribution transformer. And the second objective is to use the neural network that we obtain to analyze DR connection requests, DR hosting capacity, and operating envelopes. So next slide, please. So in here, what we are plotting here is the training data. In the upper plot, we can see active power. Negative values are injection of active power and reactive power. In the middle plot, we can see the reactive power, and in below, we can see the voltages for all customers. So from active power, we can see that around 8% of the single phase customers are equipped with PV systems, and we can clearly see the 5 kVA export limits for all the customers. In terms of reactive power, we can see, as Dylan mentioned before, that we observe absorption and injection of reactive power through the entire day or the entire period, and we see also a variety of voltages for all customers. Next slide, please, Nando. So in here, again, we see what we see here are the plots for the test data, active power, reactive power, and voltage magnitudes. And the important thing to highlight here is that the test is basically representing different behaviors of demands, different PV generation because of the irradiance, and different reactive powers behavior absorption and injections also. So next slide, Nando, please. So let's go to our neural network selection process. So as I mentioned before, the first step for the neural network selection is to define those hyperparameters that are given by the characteristics of the problem. So the input light dimension is going to be 2 times the number of per phase NMI devices, as I mentioned before. So it's going to be 396 for this particular case. The output light dimension is going to be 1 time the number of per phase NMI devices, which is all voltages in the network, which is 198. We are going to use a linear output activation function. The loss function is going to be the mean square error, and the optimizers is going to be Adam, as I mentioned during the methodology. So next animation, Nando, please. So with these hyperparameters and characteristics defined, we are going to define our hyperparameter search spaces for our K-fold cross-validation. So as we use 6 weeks, the K for the K-fold that we are going to use is equal to 6, and each fold is going to be equal to 1 week length consecutive. The number of hidden layers, we fix it into 1 because to maintain a lower, to keep tractability over the search spaces that we are going to generate. The number of neurons is going to be always proportional to the number of per phase AMI devices in the low voltage network. In this way, we can scale our methodology to any type of low voltage network, to any type or size of low voltage network. The activation functions that we are going to assess are hyperbolic tangent, switch, and ReLU. We are going to analyze different learning rates, different batch sizes, and different number of epochs. So in total, we count with more than 1,000 hyperparameters combinations for which we are going to train 6 neural networks each. So a lot of neural networks for this part. So next animation, please, Nando. So with this, we can define the best hyperparameter combination. With this hyperparameter combination, what we are going to do is to train 10 neural networks from scratch using the entire training data. And we can define our best neural network based on the root mean square error for training. So with this, we define the best hyperparameters for this type low voltage network, which is 10 times the number of per phase AMI devices in the low voltage network, which is 1,980. We are going to use the hyperbolic activation function, a learning rate of 1 exponent minus 5. We are going to use a batch size of 72, which is equivalent to 6 hours. And we are going to train our neural network through 2,000 epochs. So next slide, please. So in here, we present the results for the final neural network. In the left side, we can see the results numerically, whereas in the right side, we can see a violin plot for the voltage deviation. So let's go part by part. In terms of the numerical results, we can see that for all customers, for all 170 customers, the root mean square error that we obtain for the test set is 1.25 volts. The average deviation that we obtain is 0.99, which is really accurate voltage calculations. It's less than 1 volt. And the maximum deviation is up to 8 volts. So in the right side, what we see here is a violin plot in which we plot the voltage deviations, which are calculated as calculated voltages minus actual voltages. And in here, we can see that 50% of deviations are located within a constrained range, which goes from minus 0.86 to 0.82 volts. So it's a range of more or less 1 volt. So in general, we can see that we obtain accurate voltage calculations, achieving an average deviation of less than 1 volt. Everything is out of a round of the nominal value, which is 230 volts. Next slide, please, Nando. So what we see here is the time series plots for our voltage calculations. So in the red dashed line, what you can see is the Victorian statutory limit, which goes up to 259.9 volts. In gray, you can see the Australian statutory limit, which is 253 volts. Whereas in black and in purple, you can see our actual voltage values and our model-free voltage calculations. What we plot here are envelopes for the time series, all right? So for black and for purple, what you are seeing, the region that you see color is the difference between the maximum voltage at that particular instance and the minimum voltage at that particular instance. And we can observe with our time series results that we can obtain accurate voltage calculation. So, perfect. All right, so we have our model-free approach, and we can see that it can produce accurate voltage calculations. So now let's use it. Next slide, please, Nando. So the first application example that we are going to present today is a DER connection request. So the idea here is to carry out the assessment of a 5 kilowatt PV system for a particular customer. So the consideration that we take for this particular study in defining the scenarios, as Nando was presenting at the beginning, we consider all customers with a low demand, because we are trying to assess if we can host a 5 kilowatt PV system. So we are going to consider a time or a recreate scenario in which we have high irradiance, like high export, and low demands. So we consider a random values for all customers for active power between 0 and 1. And I want to be super transparent in here. We use random values between 0 and 1 because basically what we could have done in here is just to use like really small values, like 1 kilowatt for all customers at the same time. But we have seen some limitations for the neural network when we use these values, because the neural network hasn't seen all customers with the same values in a particular instance before. It's something that is not going to happen in real life. So the neural network can calculate some funky values when we put this particular scenario, which is a challenge that we are addressing. So we use random values between 0 and 1 to express low demands, and we consider a power factor a unity power factor. The single customer that we are assessing, we consider high export, which is -5 kilowatt. So we're going to assess two particular cases. The first case is a customer with low voltage profiles, which is closer to a transformer. And the second case is a customer with high voltage profiles, which is located far from the transformer. And the check that we are going to do, as Nando was presented before, is we are going to see if the maximum voltages of all customers are going to be within statutory limits. We are considering the Victorian statutory limit for this particular study, which is 259.9 volts. So next animation, please, Nando. So we do the check to see if voltages are okay. And what we obtain for case one is that, yes, this particular customer can host a 5 kilowatt PV system without creating issues, without creating voltage issues in the low voltage network, because the maximum voltage that we can find here is up to 254 volts. Whereas for case number two, we can see that no, this customer cannot host a 5 kilowatt PV system because the maximum voltage of some customers go way beyond to the statutory limit. So as we can see, and as the physics says, the customer that is closest to the distribution transformer can host this 5 kilowatt PV system, whereas the customer that is located far from the transformer and has a higher impact in voltages cannot host this 5 kilowatt PV system. So we can see that DR connection requests can be assessed extremely fast. This study takes less than 0.1 seconds for each of the particular cases. And to make some, to give you some sense of what we are talking here, the powerful calculations for this particular assessment, it will take a couple of seconds. So we are 2 orders of magnitude faster than the power flow for this particular situation. So next slide, Nando, please. So the second application example is going to be DR hosting capacity. So now we can see how many customers can host this 5 kilowatt PV system within our low voltage network. So we are going to use the same considerations than before, and what we are going to analyze are 4 scenarios of increasing penetration of customers with PV system. So we consider 10%, 20%, 30%, and 40% with customers with PV. And again, the check that what we want to assess is to see if the maximum voltage of all customers is within statutory limit. So next animation, please, Nando. So we want to check if voltages are okay, and the results that we obtain in here is that up to 30% of PV penetration in our low voltage network, we do not observe voltages that go beyond statutory limits. So for the base case, scenario number 1, 2, and 3, up to 30%, voltages are within statutory limits, whereas when we increase the penetration a little bit over 30%, voltages go beyond statutory limits, as we can see here. So next animation, please. So again, this is we can assess super quickly DR hosting capacity. We can do DR hosting capacity assessment super quickly, a few seconds, depending of generations and the assumptions. Next slide, please. So the final example, the application example that we are going to present today is operating envelopes. So what we want to do here is to calculate operating envelopes. And we are going to present specifically the case of export limits. So we use the same considerations as before for passive customers, which are not the customers in which we are calculating the operating envelopes. And we consider 30 active customers. The operating envelopes that we are going to consider are equal opportunity. It means same operating envelopes for all customers. This is just for simplicity and to illustrate the case, all right? So we are going to make a progressive assessment of export for our active customers. So we assess 1, 2, up to 10 kilowatts of exports. And the check that we want to do again is to see if all voltages are within statutory limits. And well, we make the checks, voltages are okay, and we can see our results. And we can observe that our 30 active customers could export up to 5 kilowatts without creating voltage issues within our low voltage network. Whereas when we go for 6 kilowatts of export for all our 30 customers, we have voltages that go beyond statutory limits. So the operating envelopes for this particular case will be 5 kilowatts. Next slide, Nando, please. So again, super quick operating envelopes calculations. And now I'm going to leave you with Nando for the key remarks of our presentation.
All right, thank you very much, Vincenzo. Just something that some of you might be wondering. I mean, how come, in the other case, that we were doing the PV connection request for one customer, 5 kilowatts impossible, and now 30 customers can do 5 kilowatts. Oh, these are different customers, of course, right? So that's the case. So how many customers do we have in this network, Vincenzo, again? Just remind me.
170.
Exactly, 170. And then for the first case there that we presented for the PV connection request, that was the worst case scenario customer, the worst voltages that we found, in terms of the lowest. So we knew that it was going to be the proxy of a customer that is very far away from the transformer. In this case, these 30 customers were just randomly selected, for the operating envelope. So different scenarios, not the same. Anyways, thank you for that, Vincenzo. So let me just finish with some key remarks, and we will have time to go through some of the questions. Very interesting questions, by the way. Thank you for the contributions there. And well, first of all, the initial findings. I mean, again, we haven't finished this project, and we're super excited, to really share all of this with you and the world. We do think that this might be an interesting avenue, for the calculation of voltages, which in turn means the calculation of many other things, such as connection requests, hosting capacity, operating envelopes, you name it. Export limits, settings because of the export limits or import limits. I mean, all the shebang that it was about calculating things because of voltages. Now we can do it just with the smart meter data, but of course, using some clever stuff. Now, I do believe that the model-free future is possible, of course. This is not to say that we have to get rid of electrical models. We still need electrical models, of course, but we need to understand the fact that there will be limitations on those electrical models, and there will be opportunities for model-free applications, right? The neural networks, as we're showing today, they are able to capture the physics. Now, of course, if you go to some of our papers that we have already published, we have used synthetic data with actual electrical models, so all perfect. The reality is that capturing the physics of LV networks with real smart meter data is much more challenging. However, it's not impossible, as we are showing today, with the data from Gemini. Now, once a neural network is ready, of course, it becomes an alternative to calculate voltages. That's what we've been preaching so far. And also the fact that it's extremely quick, faster than power flows. And that is fantastic, I do believe, the moment that we are really looking at calculations that are for thousands and thousands of customers. Now, there are many challenges, and I'm listing just a few here. Our colleagues from the companies that are working with us, they have a bigger list for sure. But I just try to summarize some of them. So the first one, which is one that I already mentioned earlier, is what is the minimum data that is needed, right? So when I say the minimum data is, how many weeks, how many months do we need? And it has to be valid, of course, after all the filtering that we were mentioning as well. So far, we are kind of heading towards a few weeks. This is ongoing research. Actually, in the morning, we were presenting some of that research, to our industry partners. And sounds interesting, that it is just a few weeks. Why? Because handling large volumes of data can be complex. And also the fact that networks can evolve, sometimes rapidly. And therefore, you don't want to really wait a whole year, to produce a neural network. So you want to just do it relatively quickly. Now, what happens with topological changes? Because they do happen. Well, as any other model, if you think of your electrical model, you need to update it, right? So the neural network will need to be updated. Now, the advantage of the neural network, perhaps, is that we might be able, with a neural network that has already been produced, to flag that topological changes have happened just based on the statistics of the numbers that we will be recording. So there's an opportunity there as well. Now, extrapolation has limitations. What do I mean by extrapolation? Everything that we say about the neural network once it is trained, all right, is about what the data that has seen before, right? Okay. Now, when do we say let's do operating envelopes or let's do a calculation of hosting capacity, this is extrapolation because now these are values that the neural network hasn't seen. And there are limitations, of course. Sometimes you can get nonsensical results. So we are doing more research to really try to understand and flag these potential nonsensical results. What about square networks? For those of you that are not really power people, single wire error return. These are very common networks that we use for rural areas mostly. And these are not three-phase networks. Actually, as a matter of fact, they're very different. And people do have smart meter data as well there. How do we do it? Can we actually apply these sort of techniques? Well, that's a question mark. I think it's tricky, but I don't think it's impossible. Well, with that, we are finishing now, and then we can move to the questions. We have a few minutes, of course. All the slides are going to be made publicly available. All the links there to our reports that has been released just yesterday. That's a report there with much more details there. I just would like to thank C4Net for the funding. Of course, John, Toby, Tan from OSNet, United Energy, and Gemina, respectively, for their support and continuous guidance in terms of what really the challenges of the companies are, the data, etc. It has been a fantastic journey and continues to be. And thank you to the Melbourne Energy Institute. With that, we move on to the Q&A session. I do see here that we have a chat combined with the Q&A, so we have a mix here. So what we're gonna do, I'm gonna just go through some of the questions and I'm gonna point to any of the speakers that can actually provide the corresponding answer. So bear with me there, Vincenzo, Dylan, Chris, and Tansu. All right, three-phase customers, three-phase content. Yep, that you answered that one. This was a question for Peter. Sarat has a question: how are the research managing issues related to smart meter data errors? Yeah, that's exactly what we were presenting with the filtering. Yes, there are errors, Sarat. Actually, is asking about the future work with margin error for incomplete smart meter data. So as of now, and this is a question actually that someone else was asking as well in the actual Q&A. So what happens when you don't have the data for one of the customers out of 100 or out of a dozen in that particular LV circuit or the set of LV circuits corresponding to a transformer? At this stage, we are not considering that scenario, but we are very aware that that scenario is a reality in some cases, okay? One, because of metering issues, or second, because that particular meter is not managed by the distribution company, right? So how do we deal with this? So this is part of the research. So we will try to provide some answers on that. But right now, everything that we're doing, we're trying to create the foundations of this type of research, this avenue, of doing these model-free calculations, considering all the data available. And we were lucky enough, that OSNet, United Energy, and Gemina were able to pinpoint circuits with all the data available. Yes, with some challenges there that we needed to filter as we were presenting, but all the customers are available. So all the data points or for all instances that have been used are available in this case. So moving on with another question here, we have Liam. Oh, this is moving too quick. Have you done analysis of running model with less than 100%? Okay, that was the answer that I just gave. Sarah, how LV-based PV inverters expected to provide reactive support with voltages? Well, that is not a question really, Sarah, about what we are doing. Actually, as a matter of fact, some of the photovoltaic inverters, as Dylan was presenting, they are already providing reactive power support, because here in Victoria, that is also has been updated recently in the Australian standard. Photovoltaic inverters do volt var and volt watt simultaneously. So you can Google that and find where we even have projects there that we have presented that. So that is already happening, and that doesn't matter because the smart meter is recording everything and the physics can be captured. Then swear, I already explained what is swear, single wire return. Thanks for those of you that actually provided that. Peter, all right. What are you asking here? Thanks for joining us, by the way, Peter. To say that you big voltage regulation of maximum customer to 60. The direction code specifies, yes, 253, 99%, and 1% of the time. The level of customer requirements damage and is responsive to all. Or is so long maximum voltage is below is likely to result. Okay, fair enough. You're talking about the 99%. Yeah, Peter, I appreciate the actual clarification there. Thanks for that. Yes, it's the 99% and the 1%. So perhaps that's something that we need to clarify there. Thanks for that, Peter. I appreciate that. Sarah is asking, will a few weeks of data be sufficient to capture? So Sarah, so that's part of the research. So far, what we didn't present that here. We are seeing that around 3 or 4 weeks might be enough. However, when we say 3 or 4 weeks, this is 3 or 4 weeks of 5 minute resolution data that is considered valid. Which means, if you might remember the table that Dylan was presenting, after the filtering, it became 60%, 70%, different values of valid data. So perhaps we might need to request, 5 or 6 weeks to then, get to the 4 or 3. All right, so it depends. But we are trying to answer that because that's very important as well, the moment that we move to operationalizing this idea. Marcel is asking, with energy storage and energy storage are international constraints, how will they handle the storage assessments? No, there's no problem whatsoever because the electrons don't care where it is coming from, storage, from electric vehicle, from photovoltaics, from the house, from your kettle, from your shower. It doesn't matter. Electrons are electrons. And the electrons are going to produce, the readings for the smart meter. So it doesn't matter the technology. The smart meter will have the corresponding voltage and currents and the corresponding angle there that then we will translate to P, Q, and V as we were explaining. So it doesn't matter what technology is connected to the house. What matters is the network is the same throughout the period of the historical smart meter data. Now, moving on to the Q&A, I'm going to close my chat there because otherwise we don't have the time. I really wanted to answer the questions from the people that really use the Q&A. So we have Brad asking about step 7. Vincenzo, that's for you.
Yes, it is correct. For step 7, you train 10 neural networks for initial weight sensitivity. That is correct. And in terms of running the second question that is there, in terms of running 10 neural networks, basically what we do is 10 neural networks with all the training data and the same hyperparameters. So it's not part of the k-fold, it's after the k-fold with which was select, and it's all the aim of this is initial weight sensitivity. Yeah, that's the answer.
Thank you. Then we have the 10 training sets also from Brad. You have any comments there?
Ooh. No, it's the same. It's a confusion. Yeah.
Right. Okay. Step 7. All right. Okay. Yeah. Good. No worries. Now, Bernard is asking how does model-free approach black box model compared to LV electrical model using data? Well, so you can go to our papers. Actually, we have done this because what we presented today was real smart meter data. And because it's real smart meter data, we don't have the real network, all right? The real network, that's the whole point. You don't have the real network, and then this is a challenge. So we have compared with actual electrical models, but all synthetic data in our paper. So you can see the comparison. Actually, the results are even better, to be honest. The moment is just a perfect electrical model against, and then the corresponding synthetic data, and then extracting the neural network or producing the neural network from there. Now, however, we are also part of another project. It's called Project Edge, where we are doing the calculation for operating envelopes using actual electrical models, but we are going to test as well because those electrical models have been validated as part of the project. So we're going to do some tests so we will be able to answer better that, Bernardo. But at the moment, you can go to those papers and you can see, with synthetic data, what will happen. With synthetic data, everything is a little bit more beautiful, though. Brian is asking access to data. No, that we cannot answer, unfortunately. That's for C4net. Alex, why not use VNI? So Alex, that's an interesting question. When you run power flows, you don't specify a house consumes 16 amps at 216 volts. You don't do that. You say a house consumes at this moment in time 2 kilowatts with a given power factor. So therefore, P and Q is extremely important because at the end of the day, the application here is about hosting capacity, operating envelopes, connection requests. It's about P and Q. So that has to be the input. cannot be VNI. That's a reason. Are you exploring ways of automate data curation processes? Well, perhaps. We are not exploring at the moment because we're focusing on the core part of the project, but yes, there are opportunities for data curation indeed. Brad is asking to consider using distribution for each customer using input based on historical data. Yeah, that's a good one, actually. That's a good suggestion, Brad. This is relatively recent that we notice, the funky results the moment you have just values that are flat to the application that we were presenting. But yeah, that's you could extract those distributions based on the historical data. That's a good point. Liam, apologies. I mean, we're exceeding a little bit the minutes of the webinar, so we're going to stay just a few more minutes, but we're going to finish very soon. Of course, I do want to go through your questions. Liam is asking here, have you done analysis already? Okay, less than 100% of it. So Liam, this is related to what I was mentioning earlier. Right now, we are considering we have all the data for all the smart meters, for all the customers. We were very lucky, to work with the companies here that I mentioned, John, Toby, and Tan, and they and their team, did a fantastic job in gathering the data, and that is working. This is our starting point, so we can prove the concept. The next stage, and it's part of the project, is to understand if we can deal with this with less data, because that will happen for sure. Brad is asking, are you considering a Monte Carlo approach for switching over to multiple simulations? Well, I mean, at the end of the day, yes. I mean, how you want to apply your hosting capacity, for instance, it can be with Monte Carlo, but then the Monte Carlo doesn't take away the model-free approach, right? Because the Monte Carlo, you can do it with power flows as well. So that's separate. Peter is asking, how do you reconcile one customer at the end of the line, 5 kilo breaching voltage within the hosting capacity allows up to 30? Oh, that's what I explained already. That's because that case was the worst customer that we picked, because that was the idea based on the voltages. But then, of course, in the moment of the hosting capacity was all the random customers, so different customers, Peter, in that case. We cannot tell you exactly where they are because we don't know exactly. We don't have the nether, right? So that's the whole point here. Vinci is asking, have you had the chance to try this model, the square lines? No, we haven't, because all the data that we have collected was for 3-phase low voltage networks. We might explore the square lines, as I mentioned at the very end. They are a different, kettle of fish. It would be very interesting, but right now the focus is on the 3-phase low voltage networks. Bernard is asking if we compare the hosting capacity results using the proposed model for approach or results that can be obtained in the traditional method. Well, the thing is that you cannot, because you don't have the electrical model. That's the whole point here. However, as I was mentioning, we have done some comparisons with synthetic data from electrical models, all simulations in some of our papers, and also we will do some tests, with Project Edge networks, where validated networks. So that would be very interesting to share. Ashok is asking, Simon, do you have the possibility of maintaining digital twin of a distribution network? Yes. Well, I mean, it depends on what you want to call a digital twin. It's a digital twin because of the impedances and topologies, or a neural network. This is the neural network-based digital twin. That's what we're trying to say. Brian, you're asking a few things here. Okay, have you considered the voltage at the reference bus? Yeah, that's the beauty of what we are presenting today. There's no need of the voltage at the reference bus, because it is inherently captured by the smart meter. So you don't need it. Now, of course, the moment that it is extremely different from what the smart meters have seen before, then we have an issue. So we have in some of our papers, if that data is available, actually the neural network can get even better. But the reality is that data is not available, because in the world, it's not common for distribution companies to put a meter there. It might be in the future, and that's great, extra data, but not today. Have you compared the accuracy of neural networks with various structures? We have. You need to go to our papers, and the one that we submitted will be more comprehensive, but we cannot share it because, of course, it's confidential. Apart from the topology change, what about impacts of new PV installations? No, that's more electrons. They will not have a significant impact. The most important thing is that the network doesn't change. Now, eventually, there can be impacts because of the changes in injections or absorptions, with an electric vehicle, depending on how the meters react to that, because unfortunately, well, the meters are not perfect. But in general, we don't expect significant changes. The big changes are with topological changes. Christian is asking, how do you decide which customer gets to have photovoltaic? No, that was just random. That was just random. I was just playing, Christian, really. It was just as an example, really, just only that. Brian is asking, agree with perhaps electrical model free, but it's impossible to extrapolate or take it without. Yep, I know. There's a risk of being deceiving by talking about model free. Yeah, I know, Brian, I understand. There are models, of course. The neural network is a model, but considering that it's a very different model, so we decided just to call it model free. But it's, precisely speaking, would be an electrical model free because you need the model in your network. Then why neural network or not super vector machine? Well, I mean, where it is something interpretable or not, it doesn't matter. I mean, there are multiple machine learning techniques out there, and actually we are testing many of them as well. But we felt that this was perhaps one of the winning ones, but we are testing other ones anonymous. And then that's it. We cover all the questions. Shika, sorry that I extended the time so much. Any final comments, Tansu or Chris? No. If Shika, back to you.
Thanks, Nando, and no worries. And thank you, everyone, the presenters for the great presentation, and for all of the participants and attendees on the webinar. Thank you for hanging out for a couple of extra minutes. We know that the Q&A is really where you get to kind of get into the nitty-gritty about some of the applications of the project. So look, great presentation. I think it demonstrates, you know, some of the challenges and great opportunities that exist during the energy transition. And we're really lucky that a lot of this transition is happening coincidentally with the explosion of big data, and particularly through smart meters and IoT devices, so that we can leverage that those resources in understanding how to integrate more DER, harnessing that data and maximizing its utilization really raises these opportunities to inform both evidence-based policy, which is something that C4Net, you know, strives for, and providing business and customer insights as well as operational insights, and opens the door for the opportunity for new products and services. So we know that AMI smart meters are bearing fruit in practical ways, such as the applications that Nando and his team have presented here, and quicker assessments by the networks will allow for better and easier business case analysis to support localized renewable energy sources and multiple market participation scenarios. C4Net is really supportive of the applied research projects, such as this one on model-free or electrical model-free operating envelopes, as we might start calling it, and welcomes approaches from anyone on the webinar, any stakeholders around challenges that can be addressed through research ideas. And we're committed to maximizing the use of data to support all research efforts and support evidence-based policy reforms. So we just want to end on the note again. Thank you so much to Nando. Thank you for the comprehensive presentation by you and your team. And thank you to our DNSP members, AusNet Services, Gemina, City Power, Core United Energy. We've recently launched through C4Net our data access services, which provides access to data for over 60% of all smart meters that have been installed within Australia and are in Victoria. And judging by the response to date, there's a real appetite for this kind of electricity data to inform how to address both customer needs and engagement, power systems challenges, network hosting, and all of the other challenges that we know are occurring in the sector, and opportunities. If you're interested in learning a little bit more about this DAS service, please feel free to reach out on our website, or you can email us at data@c4net.com.au. I've posted that in the Q&A in the chat. We're building on this service. We're promoting our EV data warehouse, which is in its testing phase currently. And we're really keen to hear from all of you on any needs or contributions where data can support research in this area. Again, thank you to everyone for your participation and contribution today. And we look forward to seeing how this research progresses over the next several months, and looking forward to the next webinar and our reports. Thank you to everyone.
Thank you very much. Bye-bye.
Everyone.